Okay, so let's talk about the nonlinear Schrodinger equation. Um, the, the equation is going to be ETU equals minus Laplacian of u minus lambda u alpha minus 1 u of x 0 is equal to u naught of x. Okay, and t is in R, x is in Rn, okay? And lambda and alpha are real constants. Alpha is greater than 1, okay? We shall say that the equation is focusing if lambda is greater than 0. This is an attractive nonlinearity, and defocusing if lambda less than 0. This is a repulsive non-linearity. Okay. In any dimension, the equation in the focusing case, lambda greater than 0, has solutions of the form uxt ei omega t phi x. Okay. This sometimes I call standing waves or ground states. Okay, so what happens if we put this or this right in here? So we will obtain what is called an elliptic problem of the type minus Laplacian u f u. Okay, because if we want to obtain this, then we will have minus Laplacian u equal to minus I dtu plus lambda u alpha minus 1 u. Okay, so this is going to be our f of u. Okay, so what we'll have if we put this here, then well, we will have to derive t here, obtaining I multiplied by I omega ei omega t phi x equals to, okay, minus Laplacian ei omega t Laplacian phi. We put a minus here and minus lambda. Well, in this case we will have this inside, alpha minus 1, and well, again, omega t phi x. Okay, so we can get rid of this, and finally we can say that we have minus Laplacian, okay, plus, well, omega phi, and equal to lambda phi x alpha minus 1 phi. Okay, and now we want to consider the solutions of this problem with omega positive and lambda equals to 1. Okay, so this is going to be the problem of to find phi in H1 Rn such that satisfies this equation. Okay, so there is a theorem about this. Let n greater or equal than 2, and we will set that alpha is going to be between 1 and a condition that depends on n. Okay, then there exists a unique positive, let's say spherically symmetric solution of, well, the problem that we said before. Let's say phi in H1 Rn, and moreover phi and its derivatives of up to order 2 decay exponentially at infinity. Okay, so this is going to be solution of the problem minus Laplacian phi plus omega phi equals to alpha minus 1 phi. Okay, so we can use the invariance of the equation to generate other solutions. So if U is a solution of the nonlinear Schrödinger equation, then the following are also solutions. Let's call U mu xt is equal to mu 2 over alpha minus 1 U mu x mu t squared here, and mu is a real number with initial data given by u naught mu, okay, of x is equal to mu 2 over alpha minus 1 u naught mu x. Another type of solution, u theta xt is going to be equal to ei theta u xt theta real number. Okay, I forgot to say this one is, the first one is called scaling. The third one, ua of xt is going to be equal to ua is an a xt a any square matrix orthogonal matrix. Okay. Fourth one, u a b of xt is going to be equal to u of x minus a t minus b, a real number, Rn, and b a real number. Okay, another type of solutions, uc going to be equal to EICX E minus I C squared T multiplied by U of X minus 2TC comma T, and this is for C in Rn with an initial data UC of x0 equals to ICX U naught of x. Okay, this one is called Galilean invariant. Okay, a sixth property or solution. But this is if alpha is equal to 4 over n plus 1, then we will have a solution u omega xt equal to 1 over alpha plus omega t n over 2 multiplied by e to the I omega x squared for alpha plus omega t. Okay, and then we'll have here multiply by u gamma theta t alpha omega t comma x alpha plus omega t with a multiple by alpha theta minus omega gamma equals to 1. This one is called pseudo conformal invariant solution. Okay, so having all these types of solution, one can have a multi-parametric family of solutions. It's called R that depends on b omega theta x naught. Okay, in this case we will have that b and x naught in Rn, and omega greater than 0 theta in R. This family of solutions is going to be the following way: EIBX minus b squared t plus omega t plus theta 5 x minus x naught plus 2bt. Okay, so notice that this is like a solitary wave that moves on the line x equals to x naught plus bt. Okay, so the existence of solitary wave describes a balance between nonlinearity and the dispersive character of the linear part. We already know that when we had EIT U naught solutions for the linear part, let's say that U naught in L1 and in L2, then we had that the solutions decay as t goes to infinity for f in L1 and L2. Okay, but it's not going to be the case for the nonlinear Schrodinger equation.